So welcome to this week's Graphics Programming Weekly. We're covering the first half of Chapter 3 of the VK Guide Vulkan tutorial, which is all about vertex buffers and push constants. So we've been hard-coding the vertices in our shader, which I finally figured out how to do in the editor last week. It was a little bit of a debacle when I couldn't get the shaders working, but I digress. In the graphics pipeline, we generally use vertex buffers to store vertex data, specifically the positions, colors, and normals of vertexes in a mesh. Need to store that vertex data somewhere in memory that's visible to the GPU, and therefore that we have GPU memory. And there's only two kinds of GPU memory in Vulkan: VK buffers and VK images for images and buffers. We've already been using images for a little bit, but we haven't dived heavily into them. We've just been using images that are taken from a swap chain. We'll use them in a bit for depth buffer and textures, but we don't need them for now. We just need VK buffers. There's multiple kinds of VK buffers, though they tend to be just vertex, index, and uniform. And even some hardware, it doesn't actually care what the kind is. We have to set up our pipeline to accept the vertex buffer with the layout we need. This will be the vertex input state. This is where we'll specify what the size of the vertex is, the type of information is in it, and the stride and the position and the biting and all sorts of fun things. It's extremely similar to DirectX and OpenGL because, as it turns out, the hardware is rather similar, at least as far as the API goes. So if you are familiar with OpenGL or DirectX's model of vertex buffers, in Vulkan, we do have to allocate memory. Laser, you're being a little bit loud. Don't see a way to mute. Anyways, so in Vulkan, we have to allocate all the memory we want to use by ourselves. We don't have the driver doing it for us. It's not that hard to create your own allocator, but it's a bit of a chore, and we're going to use the VMA or Vulkan Memory Allocator library to abstract it away from us. We need to use an allocator, not just for performance reasons, but specifically because Vulkan limits the number of allocations available, or Vulkan allows there to be a rather limited number of total allocations, somewhere in the 4096 or even lower range. I believe this 1024 is not accurate, but you don't want more than a couple hundred individual allocations. When I say allocation, I just mean a allocated memory range. That doesn't mean VK buffers inside of it, because you can have multiple VK buffers in a single allocation. But since we're using VMA, it's going to manage that for us, and we're not going to have to think about it. We still need to understand that memory in Vulkan can come from multiple places. Not only is there a GPU and CPU RAM, which are separate, there are separate types of GPU memory or CPU memory, which have different properties and flags, and these get exposed as heaps. So we'll want to allocate memory from the appropriate heap. The VMA library lets us dictate which heap we want, either using helpful abstraction over the different types of heaps, or you can directly specify it, though I forget about how to do that. So we have to specify the vertex input layout. I just grab that above. Yeah, I described how to do that, and now we are going to go do that. To use VMA, we have to create the VMA allocator. So we need to create a VMA object and initialize it. And we can do it right in the init function. Yes, plain format. Do your thing. Since we're not, doesn't need to be a separate function. If I try to compile and run the program, I first need to include the memory allocator in the header. And it should compile but fail to link. Let's see what problems it has. Yeah, it failed to link. So this is a bit of a C++ and C quirk. The VMA library is a header-only library. If you include the header and we go to it and get past all the documentation, all we get by default is the type definitions. We don't get any of the function definitions. To do that in one file and one file only, one file being a C++ file, not a header file, we need to include the Vulkan memory allocator with this macro defined. So headers are just copy paste includes. So this header file is like when you pound include is just being copy pasted in. The same thing happens here. But since we do this macro define, it will do the right magical stuff inside of it to define all the functions. And so when we hit F5, it should now compile and run. With that out of the way, we're going to make two new files, vktypes. Oh, there already is a vktypes.h. Oh, we're going to add stuff to it. So we're going to have to, we're creating a buffer, a type called allocated buffer that holds a vk buffer handle and a VMA allocation handle. That way, when we want to manage the buffer, we have the allocation it was allocated from right there. It's very similar to a VK buffer and how you use it. You just need to keep track of it, and it's easiest just to bundle them together. This is the file we're going to create. I jumped the gun in describing that. So we're going to create two files, vkmesh.h and vkmesh.cpp. vkmesh.cpp. Come on. We're going to have to add it to the source code. We don't actually need the header files here. I'm going to delete them because I feel like it. And do vkmesh.cpp. So now if I compile it, it should compile and not complain about missing things. But it also should reload the CMake project because we changed this file, and so it's like, I need to refresh the CMake project. So with that done, we can see the files here. And where's the header files? Oh, bugger.
Yeah, Visual Studio rely on CMake to have those header files so it can list those files.
But I can just open the file manually, and that'll be all. So we have a header file, gotta have the pragma once. We're going to use the VK types, we're going to use a vector, and we're going to need the vec3 from the GLM library. This is defining the vec3 type, which is akin to the vec3 in our shaders. So this is allowing us to create a C++ struct with similar characteristics to what's in the shader. And because we're going to be passing this vertex data into the shader, we want to have a struct that data type that matches it. Our mesh is just going to be a vector of vertices. Shouldn't be any surprise. And while this is our CPU storage for the vertex data, our GPU storage is going to be in our allocated buffer, which is in our VK types. So, And this will just make things happy. So we have our mesh class, and we're going to include VK mesh. Did I need to do that? Maybe not. Well, all we're doing is replacing the hard-coded positions with a vertex buffer, but in the process of doing that, it allows us to then expand our vertex buffer to contain an arbitrary number of vertices, which will be awesome for rendering arbitrary shapes and models and stuff. We will need a pipeline specific to it due to the vertex layout being different. And we'll need to create a function for loading the meshes, as well as a helper function to what was the reason? Oh, just load a mesh. Oh, upload. Sorry, I misread that to think from the disk. No, this is upload to the GPU. So this will be taking a mesh data on the CPU and transferring it over. So we'll need to call that in the startup function. We need to do it after we've created our allocator. And our load mesh function, we can throw at the bottom. Actually, not the very bottom, but here, our load mesh function, it takes the triangle mesh we have created. We resize it to have 3 vertices because we want a single triangle, and a triangle needs 3 vertices, the 3 corners of it. And we specify the coordinates of each vertice. We're also going to specify the color, but since we just want a green triangle, they're all going to have the same value. And then we call upload mesh on it. Here we go. The function itself is a bit complex. We have our VK buffer creation information. So buffer create info, got the S type. We need to set the size in bytes. So we have our size is going to be the number of vertices we have, i.e. the size of the vertex vector, times the size of vertex, which this will get you, I think, 12, because if we look here, GLM vec3, that's a vector 3 component vector, an x, y, and z of where each component is a floating point value, or 32-bit float, that is. So it'd be 3, 6, 9 floats times 4, which is 36. So that actually should be 36 bytes per vertex, and then we have 3 of them. So I'm screwed with my math. Correct me if I'm wrong. It doesn't matter, we're letting the computer do it anyhow. So here's our buffer usage. This is where you describe the different kinds of buffers. There's index, there's uniform, and there's a couple other ones. Since we're going to use it as the input to the vertex shader, we're going to use the vertex buffer bit. Since we're not allocating the memory directly, we're going to let VMA handle the buffer creation. So there's no call to VK create buffer right here, which is what you'd expect usually after a create info struct. Since we're using VMA, we need to define the VMA create allocation create info. And all we need to specify is that we're using the CPU to GPU memory usage type. There's several of them. Let's see if IntelliSense can give me good usage. Yeah, here's the different kinds. GPU only would be things that you transfer once and only once. We're going to be lazy and use CPU to GPU because it's easier to transfer the data. CPU only is if you're doing something that's only needed on the CPU. Similarly, There's several others for specific use cases, like GPU to CPU would be transferring data from the GPU to the CPU, like if you took a screenshot. With our create info for the allocation and the buffer, we pass it into the handy VMA create buffer, which we pass in our two create info structs. And then we also pass in a reference, or is it a pointer? Yeah, pointer to the VK buffer and allocation structs. And it will create it for us, put the handles into these two things, and then we add our delete function to the delete queue. So we need to call VMA destroy buffer because we use VMA create buffer on it. We have to have the buffer and the allocation used, or we got from, from create and create buffer. So this will, we have now uploaded the mesh, except we actually haven't uploaded it. We've just allocated memory for it. Now we can write into it. There are multiple ways of transferring data from the host to the device or the CPU to the GPU. For now, we're just going to be copying it directly after mapping the memory. So mapping memory is where you take, you tell the drive that, hey, I'd like this buffer to have a memory address that can be accessed from the CPU. And it will map the GPU memory such that we can then copy into it. Depending on the usage mode we've chosen, this might just be doing nothing because it's CPU memory. It's already mapped because it's allocated on the CPU host. But if it was GPU memory, then it would involve the driver hooking up the virtual function table on a drive on the device, like the GPU's VRAM, and making it accessible. So when we do a mem copy of the data, we have our vertex data here, and we're copying the size that we have, and we're putting it into the pointer that we've mapped, because to do the mapping, we need to tell the driver where we want to store the pointer to the mapped data. A quick note, if we were copying data every frame, this would actually be a fine strategy to do a map, a mem copy, and an unmap. But if you're doing that every frame, this actually takes a fair amount of bookkeeping and work. And if you're doing it every frame, there's very little reason to actually map it every frame. You just map it when you create it and then leave it mapped. But since we're using this for vertex data, we upload it once and that's it. There we go. Okay. With that, with the memory created and copied, we now need to make the pipeline accept our vertex data. So we need to create the struct that holds the specific layout of our inputs and attributes. I could read through the code and just tell you what each thing does individually. Unfortunately, it's kind of annoying to explain. Rather, this, can I make this full screen? Yeah. So this helpful diagram by David D. Gioia. I've put the link in the chat. Yell at me if you want the link again. It breaks down what's going on with these vertex input attributes and vertex binding descriptions. You can have multiple vertex buffers bound when you draw. So when you call command draw, you can have 4, 5, 6, probably up to 8 or 16 individual VK buffers bound. You can have it like that and have your positions, your normals, your colors, all your vertex data in separate VK buffers, and that's called de-interleaved data. You can also put them all into a single VK buffer where each vertex contains the position, normal, and texture coordinate, and color, and all sorts of other stuff, any other stuff in each vertex. This is a struct of array or array of structs style, where here we have an array of structs where each struct has all the data it needs. Alternatively, the struct of array layout would have a array of positions. So there'd be a position, 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 followed by normal, 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 followed by color, 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 et cetera, et cetera. That's one of the reasons why there's separate input attribute descriptions and input binding descriptions. The binding description corresponds to the overall binding the VK buffer is attached to. The input attachment description refers to the contents of the binding. So per unit or per vertex, what is in it? If you had, with what we're going to do, we're going to be copying this pretty too much to the T, say we're going to use colors instead of text coordinate. So each vertex input attribute description has a location, a binding, a format, and an offset. The location 1, 2, 0, 1, 2 should just be a numeric index increasing. This will correspond to the layout location in the shader itself. We already saw hints of that in the shader code with our layouts here. This is the fragment shader with our layout here. If I copy this, so this would be what the location in the first, the location here refers to, refer to this aspect. The binding corresponds to the overall group. Notice how all three of these input attachment descriptions have the same binding of 0, whereas over here they have the same binding of 1. Because the location is not per binding, it's global to all bound vertex buffers, you have to have the location be unique, meaning I can't have 1 and 0 and 2 reused on this binding. I have to go 0, 1, 2, 3, 4, 5. That's because even though I could have 2 separate vertex buffers in 2 separate bindings, I can dissect them like this, and in the shader, there is no distinction between the bindings. It's just one giant block of locations. For that reason, we have the location ascending linearly across all in vertex input attribute descriptions. So the format looks a bit weird because it's the same format you use for images, but in essence, the format we're using is the R32G32 B32 S float. It's a 48-bit, 48? No. It's 96 bits long vertex struct, because the size of a vertex is not a vertex. The size of a vec3 is 3 floating point numbers, and so that's what the S float is. And we have RGB corresponding to the size of the structure. Yeah, 96-bit. I figured it out eventually. And lastly, the offset is specifying where in the vertex struct does this individual attribute refer to? So this first offset is actually 0. The second offset is 12, and the third offset is 24, because this is bytes, not bits. So the offset is in bytes, and it almost always is a multiple of 4. Although I guess you could get more fancy. So the vertex input attribute descriptions refer to the individual things here, whereas the vertex binding description more refers to the entire thing. For it, it has binding, which should match across all of them, but the stride is the size of the entire thing, whereas over here, you'll notice the input attribute descriptions, the format corresponds to the size of the individual attribute. The offset of is a macro. I've seen it before. Yeah, okay, is it a standard C macro? C stood def. Well, that's useful. And I think the caveat is you can't use it if the struct is not simple, as it has private members, virtual members, anything like that. As long as it's just plain data, it should work. So yeah, it's a standard macro. I think that's enough description of that. That's one of the things that annoyed me, was how much junk gets thrown at you with all this description of stuff. And this diagram, I think, pretty clearly describes where things live and what things are. And so I don't have to go through this whole code block and try to explain what everything is. To make use of our vertex layout, we need to create some new shaders. I'm going to create my shader in the shader folder and call it try mesh.vert. And I have to rename it because I named it wrong. I'll do the other one. Try mesh.frag. Go. It should appear here if I rerun CMake. And I think I need to go to build CMake. Yeah, save. Okay. Yeah, I picked it up. Woo, okay. Here we go. Now I can copy paste the code in. So we have our 3 attributes, our position, our normal, and our color at 0, 1, 2. Oops. And we go to, where did I put that? We have our hard-coded formats for everything. Everything is the same size, at least the attributes, bindings, locations. We all talked about it. There's the offset of, and that should all work. Nice. So now we just need to get the, oh, okay. We didn't need this shader apparently. Whoops. I'm just gonna remove it and assume everything works. Okay. We have our vertex input description struct, but we need to then hook it up to the pipeline. Just copy all of this and slap it at the end of the engine pipeline code, because this function needed to be longer already. Oh boyo. Okay, this is replacing this. Yeah, okay. So we got our vertex input description struct, which contains the vertex input descriptions, this whole thing, and it sets us up to set the pipeline vertex input state create info correctly. Since it's a vector of them, we have our count and our pointer to the data. We have data and size. We use this pattern all over the place. Since we're clearing the shader stages, we since we're adding new shaders, we're going to clear the shaders we're using and load our mesh shader. Let's try mesh that we've created. Where to go? This one, which just takes a position and passes it to the output. It does not do anything fancy. We add our shaders, and we build the pipeline, and then we destroy all the shader modules and push our new pipeline onto the deletion queue. If I run this, it probably will yell at me. Yes, it will. What for? Oh, it's because I didn't delete the source code. Okay, that would explain it. And then I got to rerun CMake. Okay. The last thing we need to do, though, to make use of our vertex buffers, now that we've hooked up the pipeline, is, well, we have to use the pipeline by binding it in the command buffer. We also need to now bind the vertex buffer, because before we didn't have the vertex buffer to bind. We did have the pipeline, though. So let's go back to the draw function, which is way up here. Oh, past it. And we're going to do it. That. Same thing here. Take our new one. So we bind our mesh pipeline. We bind the vertex buffer. So we have to bind the handle, and the offset is 0 because we can bind parts of a vertex buffer as well as whole vertex buffers. And then we draw. Now, this is something I've seen happen multiple times where people will try to draw a very large vertex buffer, but forget to update the draw commands so that they're drawing only 3 of the vertices. Since we're now using a buffer of vertices, we should draw as many vertices as there is in the buffer. Why do we pass a pointer? That's a good question. Oh, yes, because this is VK command bind vertex buffers. So this could be an array and it contains many things in it. So this would be how we would pass multiple offsets and multiple buffers at the same time. There needs to be the same number of buffers and offsets. This one here refers to the number of buffers we're binding. And now we should be able to compile and run if everything went right. And we have a green triangle, which is now being taken from a vertex buffer. If I wanted to get fancy, if I could find the mesh description here, I can change this to be 0.5. And it should have a different shaped triangle now. Yeah, it's skewed. Undo that. And then we'll continue on to push constants. Push constants are the, I don't want to say easiest way to get changing data onto the GPU, but it's definitely meant to be for data that is constantly changing. A push constant, in shaders, you have uniforms, which is data that is uniform across all the invocations of a shader. So if I wanted to specify the model's position relative to the world center in my tri-mesh, I would want a uniform to store that position. This generally is a matrix 4, 4x4 matrix. And, well, we might have a lot of them, and we might store them in an array of uniforms, but what that would require is creating a memory allocation for the uniform, creating a pipeline layout to describe that uniform, and several other little bitty annoying things. Push constants offer a more streamlined way to insert a small amount of data that is uniform across draw invocations. The word uniform is a bit of a misnomer because it has some historical baggage, but I use it because it's a unique word. A shader storage object, or SSBO, shader storage buffer object, it's another kind of uniform, or it's rather another kind of way to pass data to the shader. But we won't be using those just yet. For a push constant to get its data to the GPU, it writes the necessary data itself into the command buffer. So when we're using push constants, we set the data we want in the push constant, in the command buffer itself. So VK command push constants. We have to specify the size of the amount of data we want to write into it. That way it knows exactly how much space to allocate for it in the command buffer. But this means our command data, or our command stream of our data stream of commands that the driver has to deal with also includes some additional data that we can use however we like. To specify the size and other aspects of it ahead of time, we need to declare it in the pipeline. We need to have a pipeline layout that corresponds to this. Why are you working on it? Okay, I'm going to ignore that for a little bit. The pipeline layout pretty much will only contain the push constant information. We would also store uniform, shader storage, texture, all sorts of other things would go in a pipeline layout, or at least the description of their layout of those things. But where the push constants, we're going to write, oh, I need to put this up here. Why is it data? Oh, so this is just generic data we can use. I forget exactly what we use it for. But render matrix, this tutorial, I'm going to repeat, is not a general graphics programming one. How matrix 4's transform data is for you to find out in a better tutorial that explains that kind of thing. We're going to use a matrix 4 to transform our triangle and make it spin around. We do need to create our pipeline layout before we create our mesh pipeline, so we can specify it. Go down all the way to up here. Do it after we set the shader stages, but before then. Our pipeline layout create info, we use our builder we have before, and we specify the push constants we want. So you can configure push constants pretty well. We're going to have a more monolithic approach. See, you can specify push constants that only affect the vertex and only affect the fragment shader, specifically meaning different parts of the whole push constant is used in different shader stages. What we're going to do is make the entire push constant available on the entire vertex shader. So if there were fragment shader specific parts of the push constant, i.e. what, say, like the material properties we wanted to use, we could put that in a push constant. We would have to add the stage fragment bit. And so they would be accessible by both the vertex and fragment shaders. I'm not doing that, so we don't need to do that. We add the push constant. We can have multiple ranges, but we just have the ones. We'll just take a pointer to the push constant range. And then we need to specify the pipeline layout that gets created. Oh no, we create the pipeline layout. And that doesn't get set. Where does that get set? We do need to delete the pipeline layout, but we never set the pipeline layout, do we? Or am I being daft again? Oh yeah, so we need to set it, don't we? Oh, yeah. Does the tutorial not set it here? Maybe it sets it later. Okay, well, we've defined it here in the CPU side. We need to also define it in the shader. Our push constant, it has a layout called push constant. It's a bit silly looking, but this is how we specify the data for our push constant, our vec4 and mat4. So now we can use our matrix and multiply it with our position directly. Oh, we have to use namespacing because GLSL rules are weird like that. Okay. Oh, I jumped the gun. There. So we did cover it just a little bit later. Okay. We want to set the data in our push constant every frame. That means we want to do it in our command buffer recording. The data we're going to set will be calculated from, oh, where is that? From a series of transformation matrices. We bind our pipeline, but after that, we figure out what the matrix is going to be. We have our projection view model matrix concatenation after we've rotated and done some perspective. This is a this is because we're not setting the silly Y is down thing correctly. I bet if I did this, okay, I'm not going to worry about it. Actually, I am, because that's one of those define GLM depth. Okay, I don't remember the name, and I don't want to look it up. So there's a macro you can set which forces GLM to have the Y direction pointed down, which would make this line unnecessary. What that macro define is, off the top of my head, I do not know. If I compile it, does it run? Let's find out. It doesn't. Why doesn't it? Let's do some live debugging. Oh boy. That's a lot. Oh, did I not set the, bind the pipeline? Oh, that's wrong. I need to bind the vertex buffer before I issue a draw call. That's a copy paste error. Have you ever seen one? Okay, and there we go. Slowly rotating triangle using push constants. I will say push constants really aren't great for pushing mat4s because you are guaranteed 128 bytes. Yeah. And a mat4 takes up 64 bytes. Usually you'll have your projection and view matrix separate from your model one. You'll also sometimes have a view and model concatenate. You'll have all sorts of different matrices for different use cases. And you may not have enough space because you only have space for two. Additionally, you won't be able to have anything else, at least guaranteed. There are platforms which have 256 bytes, cough, cough, a certain green team. But whether that's advantageous to have some hardware use push constants and other hardware use uniform buffers, it's usually simpler to go with a single strategy for all hardware unless you're trying to uber optimize it. So in future chapters, we'll move the matrix 4 out of the push constants, but for getting stuff moving on the screen, this is very, very adequate. And for 2D stuff where you're not dealing with map4s all the time, push constants might be all that you need. Say if you're trying to render sprites, you could just set the push constant to the bounds of the sprite, the top left and bottom right corners, and then just draw. But that's for another time. This is the end of this this session. We got through it in 50 minutes or so. Next week, we'll be doing OBJ loading, setting up a depth buffer, as well as dealing with some scene management. So some code reorganization to have multiple materials, multiple objects, multiple meshes, all that fun stuff.